an expression in our final representation and interpret it by taking capital E here, which is a polymorphic function that wants to know what kind of variable you're looking for, and tell it, please use word for variable, and then interpret that. So let's look at, well, I'll pause here right before I'm going to change up this configuration. I hope so. I hope I'm going to make this screen go up at least. We'll see. And ask if there are any questions while this code is still on the projector. Yeah?
What's the reason for doing the interp E1 in that let in clause?
It basically stands for evaluating the expression that's going to get a new name for it so that you can substitute it in for all the occurrences.
We're just kind of it's expanding all the let expressions, is it?
Semantically, we are undoing all the sharing of the let expressions. Yeah. All right. So let me show an example of evaluating an expression with that interpreter so that we can see what is happening. So there's a tradition of using these so-called Oxford brackets with brackets with a little extra line to indicate taking the denotation or the meaning or the interpretation of some syntax, and I'll use that here. For a very simple program, I'm just going to give a name to the constant 1, call that x, and then inside that body, I'm going to give a name to the constant 2. I'll call that y, and then I'll add these together using the var constructor to mention x, and then likewise for y. So this is a really simple example of syntax demonstrating how we're using these anonymous functions to model the bodies of binding constructs, where we use the var constructor at the points where we actually use any of the bound variables. Any questions about this syntax before I start computing its denotation? Yeah?
So you're using variables that look like variables, but you're actually implementing them by word.
Yeah, so I can add a type annotation here. Let's say this is a version of syntax that's been instantiated to represent variables with words, and it'll be, let's say, 8 bits or something.
And just as x is a particular variable, that's really some particular word like 003 to 001.
Right. This occurrence of x here is mentioning a particular word. And the cool thing about parametric higher order abstract syntax is we actually define a polymorphic function that lets us choose what type annotation is going to go in spots like this. It doesn't really matter. The structure of the representation is the same no matter what we pick. So we're just taking a type that the context tells us and dropping it into these positions. And in this case, I've asked to drop word in that position. Yeah?
What if we had a constant that was very large and the word was too small for it? What would happen in the group? Say I had...
The type system is ruling that out. Okay. There are dependent types attaching bit widths to everything and checking that. All right, so let's start evaluating this. So the first thing I'm going to do, the rule for let, recall, involve first, in a sense, evaluating the first argument of let. So I'll recursively evaluate const 1, and that turns out to be 1. So that means I'll make a further recursive call, or recall the rule for let evaluated this part, and then applied this function to the result, and then recursively evaluated that thing. So what that's going to give us here is I'm down to just having the binder for the constant 2 left over. And then there's an add inside of that, and a variable. Any guesses what the variable's argument is now? What the argument is to the var constructor?
What?
Yeah, good guess. For all I know, you were just going to name all the natural numbers in sequence, but that algorithm worked well. Because it's this one, not that one. I hope that answer was helpful. It wasn't supposed to be too glib. And then, what's the argument to this variable constructor?
Y.
It's just y. We haven't gotten to that one yet. It's still unknown. So we want to get the meaning of this thing. All right, so any guesses what's going to happen next?
The same like it will be 2.
Yes.
Then you replace by y.
Right, so let's say recursively we call the evaluator on the constant 2 expression, which is just 2. And therefore, I'll take us over here to another version. And now we have add var1, var2. And then things are pretty straightforward at this point. Remember when we looked at that interpreter, when we chose that variables will be represented as words, then the constant and variable cases are the same, which means in particular, if I evaluate variable 1, this is equal to 1. And when I evaluate variable 2, this is equal to 2. So then this thing will just go down to 3. All right, so I hope that shows how, first, we can make a clever choice of what a variable is represented as, and then we get this way of stepping through one particular operation on syntax, and we just have exactly the thing we want at every point where we hit a variable because we chose the right representation of variables. So again, this is the function that we just stepped through executing, and hopefully it makes a little more sense now why this works out to give the right answers. And then I'll just sort of skip past the same kind of theorem showing that this new operation viewed through the interp function gives us the same tree of arithmetic as the original version, so therefore transitively it's correct. And now I can repeat these concrete generations of code, and we're doing much better. We actually have let in preserved in that output, and it still has these little opportunities for arithmetic simplification, but we don't have the superlinear expansion by copy and paste that we got before. And even the 3 argument version is not too bad, though I had to increase the printing depth to make it all show up. Here it is. It's still linear, don't worry. All right.
Does that generate a bunch of evars for the types of the binders?
All right. If I put a little @ sign here, then it won't do that. We keep the fun binder for the variable type. If I left that off, then that argument winds up treated as implicit, and a new evar is generated to be plugged in for it. All right, so let's try to get to make these little arithmetic wastes of time go away. So to make that work, well, first, to warm up for that, let's write a program analysis. We kind of need to analyze the structure of this program to do the real operation we want. I'm just going to try to count how many lets are in an expression. And the cute way this works is I'll instantiate the type of variables with just unit. And then, well, a constant has no lets. For these binary and unary operations, just add the lets counts of their sub-expressions. Variable has no lets. A let has a let, so let's add 1 to the number of lets in this expression. And then I want to descend underneath the binder so I can count how many lets are in E2. No problem. I decided a variable is unit. What has type unit? TTS type unit. So I pass that into E2, and I can proceed without any trouble. So this function counts how many lets there are. And it's strictly simpler than the evaluator that we used before. It's using just a subset of the same tricks. So here's an example of why we shouldn't just hard code word as the representation of variables. Then we couldn't run this trick as nicely. Well, I could always just pass a 0 word down here, but it would be kind of gross. The next example shows an even better case of this, by the way. Add 2 had 12 lets, and add 3 had 18 lets. Okay, so now I want to do constant folding to get rid of those extraneous concatenations of zeros and adding zeros and all that stuff. So first I'll give us a function that's going to tell us whether an expression is a const by just optionally returning a word. This turns out to simplify the pattern matching that's going to come next. And then I won't even try to read through all the lines in this constant folder, but notice a weird thing. Variables are now represented as expressions. And the key thing this will let us do is substitute for a variable in a let by passing it an expression. So we have to reverse engineer what kind of program transformation we're trying to do to figure out why this is not a crazy choice of variable representation. So let's see this in action. Constants optimize themselves. If we have two, if we're combining, optimize both sides. If they both come out as constants, then combine them semantically, and then turn that back into a constant. Otherwise, preserve the combined constructor with the new expressions. Split 1, same basic deal. Split 2, same basic deal. Add, a little more interesting. I'm just going to check if the first expression evaluated to a constant which is equal to 0, then I'm just going to get rid of this add instead of keeping it around. So then I'll go on and simplify the second expression. There's a little bit of funny trick stuff happening here, and something I call the convoy pattern, and I won't try to explain it right now. It's all about making the type checker happy, which is a high priority. And so we optimize the second expression, the second operand. If that's also a constant, we can just run the add at compile time and turn that into a constant. Otherwise, I will add, I'll just preserve the add expression. And yeah, so we short-circuited the add if the first operand was a 0. If both operands were constants, we can do that at compile time. Otherwise, we're just recursively simplifying inside the operands of add. Here's a weird case. It's actually the same weird case as for interpreters. A variable is compiled into itself. And recall, we chose to represent variables as expressions, and that's why this works. And then in the let case, I simplify the expression that's getting a name, and if it's a constant, I just proceed into calling this function on the constant, and that function is one that recursively calls constant fold. So we just proceed into the body directly substituting in a constant without preserving the let structure in that case. And if the simplification of the first argument is not a constant, then I'll just do the usual recursively proceeding underneath the let. Where in this case, I substitute. It's kind of weird. I need to give a variable to the recursive call, and the variable I give is an expression that that just contains a variable. So notice here, there's an important kind of duality between the let in and var. We plug in a var node here, and if we get then to this case, it goes away, and this gets us back to the original structure of the expression. It's a little mind-bending, I'm sure, but it type checks, so don't worry. And then this really is an implementation of constant folding, which we'll see later. And then I can wrap this to work on these polymorphic expressions with a capital E by just building a function, a polymorphic function over the type of variables that instantiates capital E with expressions over those variables, which is exactly what cfold wanted to see. And then cfold flattens that back down to a representation where variables are just variables. And the important thing is we made variables expressions so that we could get free substitution, which if you've worked with lambda term encodings and other styles like de Bruijn indices or just literal strings, you probably know substitution is absolutely not free. Capture avoiding substitution is a pain to model. And it was free here. So that's nice. And it just required choosing the right clever instantiation of a polymorphic function so that we could get this feature for free. Any questions here? Yeah.
Is there any downside to using disencoding over the Bruijn indices, for example?
For some transformations that really do want to get very syntactic about the use of variables, then de Bruijn is easier, and other first-order encodings are easier to work with. If you, let's see, I guess that's the fundamental answer. So sometimes I translate from this encoding into de Bruijn to do, for instance, closure conversion in a functional language compiler, where you really need to know what are the variables, what are their identities. Sure. Let's see. So I should finish at 12:45, is that right?
Yeah, whenever there's an actual break for you. Or you
Well,
want to pick up tomorrow.
yeah.
Yes, right.
Okay. So about half an hour left. Let's run this thing and see that it optimized what we wanted it to optimize. This is just the latest version of the 2-digit add function rewritten in this syntax. And now all those extraneous operations at the beginning are gone. So we still are explicitly adding a 0 bit onto this thing and adding 1 onto this thing, but there's no more add 0, which used to be there. And take my word for it, or try to read through this on the spot. There's nothing too horrible happening here anymore. I think we've achieved a reasonable level of optimization, unless someone still wants to object to something here. All right, so, and the 3-digit version is only a little longer. Yeah. So I wonder what we think about the right way to prove that this optimization is correct. Any ideas how we would even state that? Let's try to work out a version I won't even try to type check here. Any ideas how we would write this statement? Yeah?
So show that for all expressions, constant folding them, and interpreting them after constant folding them is the same as just interpreting them?
Interpreting after constant folding. I'll make that a capital E for consistency with some other places is the same as just interpreting them. I think this is a completely fine statement and is indeed the good one to aim for. How are we going to prove this? Oh, question first. You're not.
Beside that, can we also guarantee that the size of the expression is going to decrease, or is constant folding just generally heuristic?
Ah, you're asking, are we going to prove this is a good optimization that actually shrinks expressions? I think we could in this case, but I wasn't planning to.
You were looking to fill 30 minutes.
You might have misinterpreted that as I ran out of content notice. That was I hope I can get to everything notice. Right, so how are we going to prove this?
Induction on E.
How do most proofs work? Induction on E. Anyone have any trepidations about running this command? Yeah.
Because expr is a for all var representation.
Yeah,
You
so
have to pick
we can't do induction on functions. So this doesn't work directly. If I try to run it, some opaque thing happens, I'm sure. That's an even lamer thing than I expected. Unable to find an instance for the variable var. I love choosing a variable named var because you get great messages like this. So this doesn't work too well. Any ideas how we can get around that? Yeah.
You choose a representation for a var, and then you apply e to it, and probably expr of actually.
But I think what you're suggesting is what's already happening. Let's just unfold these capitalized function names. We're instantiating e in 2 ways. So this is kind of tricky. We actually have 2 different expressions here. Recall when we worked through that example before, I hope I convinced you, every instantiation of capital E will look the same. There'll just be different type annotations on lambda binders in certain places. So these are morally the same expression, but Calc isn't convinced that they're the same. But I could do induction on either one of these, and then the question would be, what about the other one?
To prove a parametric induction principle.
That sounds like it's heading in the direction I had in mind. What I want to do is define a predicate that tells us when 2 expressions are basically the same except for the type of variables. And then we'll be able to use that to structure this proof. So we'll get back to this one. It's down there in essentially the same statement. I'm defining a judgment that says when 2 expressions are really the same. But it's a little complicated. Sometimes, remember when we were running the interpreter, we got to a point where we had some variables that actually take constants as arguments. In that case, we'll be comparing the interpreter's result with the constant folder's result, followed by interpreting. And then we'll have some cases where we have matching syntax trees, except there'll be a variable node on one side and a variable node on the other side, and they won't store necessarily exactly the same thing. We need to record what is our